Okay, people. So, quiz 5 due tomorrow. We've got a bunch of different stuff today, so let me just mention a few things. So, assignment 5, our very last in-semester assessment, due next week. Notice that normally an assignment, like if it was as normal, assignment 5 would only cover stuff from last week. But because I want to give you some chance to look at stuff from this week in the assessments as well, there is some material from today's seminar and from Thursday's seminar on assignment 5. So just be aware of that. Still the majority of it you can do without them, so don't let that make you hold off looking at it. That stuff is normal. Okay, so 2 other things I want to mention, only one of which I put up here. So next week we'll be doing some revision stuff in our seminars. In fact, that's all we'll be doing. So if you have requests for what things you want me to revise in those seminars, we'll probably be looking at, questions mostly, but which sorts of questions you want me to talk about. Then I've set up a thread on the forum, on the exam discussion forum for that, or if you want to email me, I am taking requests and I will do my best to cover the things that are most requested. I'll also talk a little bit in general about how the exam will run and stuff. And the final thing, which I don't have here, is please, I'll say this a bunch of times, but please fill in the SETUs, the unit evaluations. I really do want your feedback on how we could make this better, on what's going well, what's going badly, all this stuff. Yep, I think that's all. Okay. So, we're going to be talking about degree today. So, degree in a graph is a really simple concept, right? The degree of a vertex is just the number of edges sticking out of it, hopefully, as you've seen in the pre-work stuff. So, for example, here, B has degree 2 because there are 2 edges sticking out of B. C has degree 1, only 1 edge sticking out of it. A has degree 1 because there's only 1 edge sticking out of it. A vertex can definitely have degree 0, right? If it's just by itself, no edges sticking out of it, it'll have degree 0. We'll talk, may as well say this now, the biggest degree it can have, right, is, again, remember our graphs are just simple graphs, so we're not allowed multiple edges or anything fancy. So the biggest degree a vertex can have is if it's joined to every other vertex in the graph. So if your graph has 10 vertices, then the biggest degree a vertex can have is 9, right? 9 other vertices it can have an edge to. Okay, so as a bit of practice, what are the degrees of the vertices in this graph? So degree of A is 2, B 4, C 2, D 4, E 6, F G 2, H 4, I 2. Good stuff. Okay, so easy enough. Just the number of edges that stick out of a vertex. Okay, so there's a obvious but really important result, which is often called the handshaking lemma. And so what this says is that if you add up all the degrees in any graph, then that should be twice the number of edges. And the reason for this is that you can sort of think of an edge as a handshake. I think that's sort of a bad explanation. Let's go back to here. So what we're saying here is that if you add up all these numbers, 2 plus 4 plus 2, that's 8, 12, 18, 20, 22, 26, 28. Did I do that right? If we add up all those numbers, then that should be twice the number of edges. So number of edges here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Did I miss one? Because it should have been 14. 1, 2, 3, 4, 5, 6, 8, 13, 14. Yep. So in this case, 28 here is twice the number of edges here. Why is that? Well, think about what we're really doing here is counting ends of edges, right? Here, when I count A as 2, I'm counting 2 ends of edges. When I count B as 4, I'm counting 4 ends of edges. So I can do that vertex by vertex, and I get 28 like this. But I can also do it edge by edge, right? And every edge has 2 ends. So another way of getting the total number of ends of edges, which is the total degree, is to say twice the number of edges. So that's why this works. The sum of the degrees, you add up all the degrees in the graph, that should be twice the number of edges. And, of course, one really important thing that this implies is that in any graph, when you add up the degrees, that has to be an even number because it's twice the number of edges and you can't have half an edge, right? So it's got to be twice some integer. And so the notes say it's impossible for a graph to have degrees 1, 2, 3, 4, 5. Now, one reason for that is the reason we just said, because this would have total degree 3, 6, 10, 15, which is odd. That's impossible. Why else is this impossible?
Is it because of the fact that we have 3 odd pairs? 3 odd edges?
Yeah, well, so three odd degrees, meaning that the sum of the degrees is odd? Absolutely, that is one reason. What's another? Yeah, so the biggest degree I could possibly see in a graph with 5 vertices is 4. But both reasons rule it out, right? So either does the trick. So this is definitely not the degree sequence of a graph. Okay, so question 31.1 says, for each of the following sequences, either construct a graph whose vertices have those degrees, or explain why the graph doesn't exist. So which of these is ruled out by the handshaking lemma? Yeah, this one definitely, right? Because it has total degree 7. It would have to have 3.5 edges, so it's definitely impossible. Okay, why can't this one exist? Well, okay, maybe let's talk about the third one first. I reckon this one can exist. What would give me this sequence of degrees? Yeah, so a path with 5 vertices, which would be a path of length 4, would do it. Can anyone think of something else which does it? Yes, a triangle and an edge, disjoint. Right, so either of these graphs, here's one and here's another, both have this degree sequence here, right? You know, we can arrange the dots however we like, so the order here doesn't matter. And then the first sequence is impossible because in a graph with 4 edges, a simple graph, we can't have a vertex with degree 4, right? Doesn't have enough things to be joined to. Okay. Any questions on that? Good. Okay. So, the mostly true origin story of graph theory as a discipline comes from Königsberg, the German city, in the 18th century. And the famous mathematician Euler was living there, and Königsberg was built on 2 sides of a river and 2 islands. And in the 18th century, the bridges look like this. So this is the river here, and you've got 1 bank of it here, and 1 bank of it here, and 2 islands here. And in the 18th century, the bridges look like this. And Euler claimed that all the residents of Königsberg were desperate to know, could they do a daily walk, or, well, maybe not a daily walk, could they do a walk in which they crossed every bridge in the city exactly once, right? They don't have to start and end at the same place necessarily, but can you do a walk like that? So you could go like this, but then if I come back here, now I'm stuck, or whatever, right? Now, who knows if the people of Königsberg were really desperate enough about this, if they really cared. But Euler used it as an excuse to write a mathematical paper, which is arguably the start of graph theory as a discipline, I think. And so there it is. If your Latin is better than mine, you can perhaps read it. But we're not going to talk about the Latin paper, but we can talk about what he proved. So let me emphasize exactly what we're looking at here. So if I convert this to a graph, well, in fact, because of these double bridges, it has to be a multigraph. So we're going to allow ourselves to think about multigraphs just for a second. We won't do this in general, but let's talk about this multigraph. So we can see how this, if we think of A as this top bank and C as this bottom bank, and B and D as the 2 islands, then this is what Königsberg looks like, or 18th century Königsberg looks like, as a multigraph, right? And what's the setup? Well, what we want to do is we want to do a walk which uses every edge exactly once. So remember, a walk that uses every edge at most once is a trail. So the question is, can we find a trail in this multigraph which uses all the edges, every edge exactly once? Obviously, we can use vertices multiple times, right? But every edge exactly once. So that's the question. And Euler said the answer to this is no, right? And let's talk about the reason. So think about any vertex in any graph or multigraph and think about doing a walk, right? So if we don't begin or end at this vertex, right? If this is a vertex that isn't our beginning vertex or our end vertex, then what's going to happen is we're going to walk into it and then walk back out of it on some other edge. So maybe we walk in here and then we walk out here. and then if we're trying to use up all of the edges, we're going to have to walk into it and walk out of it again. But now we're stuffed, right? Because we can walk into it, but we can't walk out of it now. So it could be the end vertex of our walk, right? If we now walked back in and stopped, that would be okay. And it also could have been the beginning vertex, because then we could have used this edge to walk out of it for the first time. But because this has odd degree, right, and there's nothing special about 5 here, anything of odd degree will be trouble, it can't be, it can only be the first vertex or the last vertex. It can't be anything else if we're trying to do this special kind of trail that uses every edge. And spoiler, we're going to call that an Euler trail, right? So in an Euler, if a graph has an Euler trail, then the vertex of odd degree must be the start or the end vertex of that Euler trail. But look here, we have degree what here? 3, degree 3, degree 5, and degree 3. So we have 4 of these bad vertices, and we can burn up one as our first vertex and one as our last vertex, but the other 2 mean we're stuffed, right? So, does that make sense to people? Why this is impossible, right? So if we were trying to do this, we could have 2 vertices of odd degree or 0 vertices of odd degree. If you had 2 vertices of odd degree, you would start at one and end at the other. If you had 0 vertices of odd degree, you could start and end in the same place. But 4 vertices of odd degree means this is impossible for this reason here. That making sense to people? Okay. So our definitions are a trail that uses every edge of a graph exactly once is an Euler trail, and any graph with strictly more than 2 odd degree vertices, which is going to really mean 4 or more, right? Because we have to have an odd number of odd degree vertices because our sum of degrees is even, cannot have an Euler trail, right? And if you're looking for a closed Euler trail, so if in addition you want this walk to begin and end in the same place, then you can't have any odd degree vertices at all, right? Because then even your first and last vertex has to have even degree because you go out and then perhaps in out some number of times and then in total that's even. Make sense? So a graph with any odd degree vertices has no closed Euler trail. Questions on that? Okay, so there's this very natural thing to ask if you're a computer scientist or a mathematician and you have this sort of situation going on. You've ruled out a whole bunch of graphs from possibly having a closed Euler trail, and it's very natural to say, well, what about the rest of them? Can we rule more out, or do they all have, or do all of the rest have a closed Euler trail, right? If it fails, if it doesn't have this obstacle, so all its degrees are even, can we always find a closed Euler trail? And the answer to that is no, for a really obvious reason, right? Our graph could be disconnected. So here is a graph, all of its vertices have even degree, but of course you can't walk around it and use up every edge because you can't jump from one place to the other, right? From one piece to the other. But, okay, now you ask the question again, but with the 2 obvious obstacles removed. You say, what if a graph has all even degrees and it is connected? then can I always do a closed Euler trail. Then can I always walk around it, starting and ending in the same place and using up every edge. And it turns out that the answer is yes. Now, how would you prove something like that? How would you show that you always have a closed Euler trail? Well, you need to have an algorithm, basically. Well, you don't need to. There would be different ways to do it. But in this case, we can give an algorithm that will, a method that will always find a closed Euler trail in a connected graph with all even degree vertices. So that's what it looks like in the notes. There's a lot of words there. But it's actually not that complicated. So let me give you an example on this graph we saw before, which conveniently had all even degree vertices, right? So the way this algorithm works is it says start somewhere, anywhere you like, and just do a trail at random. So don't use the same edge twice, but just walk around, right? And eventually, you're going to come back to yourself, right? Now, why is that? Why can't I get stuck? So because everything has even degree, right, and I'm using things up two at a time, if something has an edge for me to come in on, because it's even, it will also have an edge for me to go out on, right? So I can't get stuck. And because this is a finite graph, I'm eventually going to come back to myself, right? So just blunder around, use a trail completely at random, you'll come back to yourself. So sorry, this is a connected graph with all of the degrees even, so it should have a closed Euler trail. Can we do it? Okay, so blunder around. Eventually you'll come back to yourself, right? So here's me blundering around here. A, B, C, E, D, A, right? I walked around at random and eventually I came back to myself. Okay, so that is a closed trail, but it doesn't use all the edges. And we need it to use more edges. We need it to use all the edges. So what does the algorithm says? Well, it says retrace your steps. So imagine doing this again, but now be on the lookout for a place where you could detour off, right? So at the first point, you could detour off your trail, do so, and blunder around again, right? But blunder around, don't use the edges you've already got in your trail here. Just blunder around and by exactly the same logic, you'll come back to yourself, right? So in this case, this is one way you could blunder around. You could branch off at B and blunder down to E, H, D, B, right? And what we're going to do is we're going to insert that as a detour within the trail we had before. So our trail before was A, B, C, E, D, A. Obviously, I'm just using colours here to illustrate here. Now, our trail is A, B, now blunder around the detour here, E, H, D, B, and now finish off what we had before, C, E, D, A. Does that make sense? So we inserted this piece within this piece, and now, well, this is our new trail. Now do this blundering, A, B, E, but be on the lookout for a place where you could branch off. Oh, we could branch off at E. So now do that, blunder around, that's the only thing you can do now. Insert this as a detour within your longer trail and rinse and repeat until you use up everything, right? And so the reason why this has to work is at each stage, the edges you're looking at are even degree at every vertex, so you can't get stuck. So at each stage, you will come back to yourself. And then because the graph is connected, you will always find one of these places where you could branch off if you haven't used up all the edges. And then there's only a finite number of edges, so after some finite number of steps, you're going to use up all of them. Does that make sense? So that's what the algorithm says. So I'm not going to read you all those words, right? But I think, hopefully, I just gave you the idea of how this works. Any questions on that? So because that algorithm works, provided your graph is connected and has even degrees, we can say a graph has a closed Euler trail if and only if it is connected and all its degrees are even, right? So the if comes from the algorithm, the fact that we can build them in that case, and the only if comes from, well, if it had any odd degree vertices, that in-out argument we saw says it can't have a closed Euler trail. Questions on that? Yeah.
Given an arbitrary graph, how do we validate those assumptions?
Given an arbitrary graph, how do you validate the assumptions?
You want an Euler trail, and you've got a graph, you don't know about it. How do you check?
How do you check whether all its degrees are even and whether it's connected?
Yeah.
Well, so, I mean, this depends if you're talking by computer or by hand. I mean, by hand, you look at all the degrees and you count them, and you check if it's all in one piece, and if so, it's got even degrees and it's connected. By computer, there's various ways. It's going to depend how you store it. If it's an adjacency matrix, for example, you can count your degrees as the number of ones in your various rows. Connectivity is a tiny bit trickier, but we'll be talking about ways to test connectivity in a little while. Yeah. Okay, so that is modern day Königsberg. It has more bridges now, I think, but I think this one in the foreground is one of the, well, at least in the same spot as one of the 18th century bridges. So I think this might be one of the islands, but I'm not sure. Okay, so question 31.1 says, here's the adjacency matrix of a graph. What are the, where are we? Okay. Yes, sorry, getting distracted. Okay. This is the adjacency matrix of a graph. What are the degrees of its vertices, and does it have a closed Euler trail? So what's the degree of the first vertex? 3, right? V1 is joined to V2, V3, and V5. So degree of V1 is 3, degree of V2, 2, degree of V3, 2, degree of V4, 1, degree of V5, 2. So does this have a closed Euler trail? No. It might have an Euler trail, right? Because we could say begin at this vertex and end at this vertex, and that would use up our 2. So it maybe has an Euler trail, but it definitely doesn't have a closed Euler trail, because to have a closed Euler trail, every degree has to be even. Of course, even if they were all even, you'd still have to think, must this be connected, before you decided that it did have a closed Euler trail. Okay, I've got a question for you then. So, how many of these have an Euler trail? We're not demanding closed here, but it can be, right? Euler trail could be closed or not closed. So, how many of these have an Euler trail? once you've got an idea, start asking people next to you. To know how many Euler trails there are? That's a good question, and it's the sort of thing you definitely can count in some graphs. I don't think there's sort of an easy way to do it in any graph, but we'll actually, I think we'll be looking at a question or two that asks that in some graphs. Another 30 seconds or so. Okay. So, I think we got some of you. I disagree with most of you. So, okay, so these two on the left definitely do, right? So, well, okay, so let's talk about the ones that don't. I think most people probably recognize that this one didn't, right? Because we've got one vertex of degree 3, another vertex of degree 3, another vertex of degree 3, another vertex of degree 3. So too many odd degree vertices to have an Euler trail. So this one doesn't. Now this one also doesn't. Why not? It's not connected, right? I know it sort of looks connected, but look here, this is a triangle all by itself. And in fact, it's all made up of these little triangles all by themselves, right? So this thing is just a mass of disjoint triangles, and so it's got all vertices even degree, great, but it's not connected. You can't get from one triangle to another. So I think we managed to trick a few of you with that one. So that one doesn't either. This one, it almost looks like it's disconnected, but if you follow it round, you'll see it does get round back to itself, and that is in fact an Euler trail I just traced out. The graph sort of almost is an Euler trail in some sense. And this one, also connected, also everything has even degree, so it'll have a closed Euler trail too. Make sense? Okay, I've got a second, so I'm going to say a couple more things about the SETUs to beg you to fill out the evaluations. So I've run this unit for a long time now. It's over 10 years now, believe it or not. And I really am serious about trying to make it as good a learning experience, as useful, as hopefully reasonably painless as I can. And so I really, really, really do appreciate feedback, and that there are plenty of changes that I make that come as a result of feedback. For example, the fact that you'll be able to take in a double-sided page of notes to the exam is a new thing this time round. So, you know, I do make changes in response to feedback. The other thing I'd say, this is a bit more general, is that with SETUs in general, it's worth taking the 5 or 10 minutes to fill these out. Like, you know, so it's not just me who take these somewhat seriously. Like, faculties and Monash as a whole do take them somewhat, you know, fairly seriously, I think, in the sense that if a unit gets lousy SETUs, there will be questions asked. And there are units out there, I did some when I was in an undergrad, that deserve to get lousy SETUs and deserve to have some questions asked, right? So if you think this unit is rubbish, or you think one of your units is rubbish, you should say so, right? You know, and that if enough people say that, there will be some questions asked. And likewise, if you think something is going well, then the way to try and ensure that it keeps going well and in the same kind of way is to say you liked it. So I understand a certain amount of cynicism with this, and it's not always the case that, you know, what you recommend immediately the lecturer in that unit will say, aha, I must do this, although it can happen. But definitely, you know, it's a way you get a little bit of say in what you think works and what doesn't. So I strongly encourage you to fill those out for all your units, but especially this one first. Okay, so very last definition for this seminar is the definition of a bridge. So we only talk about bridges in connected graphs, at least for this unit. But a bridge is an edge in a connected graph that where if you got rid of it, the graph would suddenly be disconnected, right? So in this graph, this thing here is a bridge because if we killed it, we'd have a disconnected graph of two triangles, right? 2 3 cycles. So in some ways, that's the most important thing here. Remember, a bridge is an edge in a connected graph where if you got rid of it, you would disconnect the graph, right? In particular, if a vertex has degree 1 in a connected graph, the edge incident to that vertex will be a bridge, right? Because if you got rid of it, that vertex would be on its own. That would make the graph disconnected. So there is this last thing, which is, well, I disagree with the notes very slightly here. So there's something called Flory's algorithm, which says that you do something similar to our detour algorithm for finding a closed Euler trail, but avoid using bridges until you're absolutely forced to. And it turns out if you do that, you don't have to do the detour stuff, right? You will actually come round and do the whole thing in one go, which seems really great. But in fact, generally speaking, the effort you have to put in to figure out where the bridges are computationally defeats the purpose, and you're better off just doing the detour algorithm, right? So unless you've got a reason to avoid, you don't want to do that detour thing, it's probably the best one. But just be aware of that as sort of a cool thing. It's one of those things. It seems very promising, seems like an improvement, but arguably the pre-work you've got to do to implement it is actually not worth the benefit in the end. Okay, so very last thing, and then we'll call it a day. So I've got this question for you. So remember, a bridge is an edge in a connected graph where if you deleted that edge, the graph would be disconnected. Yeah.
Then would it be more cost effective to use the other algorithm if you're trying to find more than one more Euler?
Yeah, I think.
Then once you find the
Yeah. So I mean, what you're saying makes a certain amount of sense in the sense that if you're going to be doing it over and over again, then maybe you only have to store the bridges once, and then maybe something like that would make sense. So yeah, no, and I mean that's a good point. In general, you know, sort of the more times you're going to be doing something, the more sense it makes to do preparatory work, right? That you only have to do once. Yeah. Is there a set value for? Sorry, I can't hear you. Say that again.
Say if n is equal to 5 in the cycle, you could remove 2 points off of each other rather than next to it, and that would disconnect the graphs. But if it's equal to 3, you couldn't disconnect the graph at all.
But where a bridge has to be a single edge whose removal disconnects the graph. So the fact that you could remove 2 things to disconnect the graph doesn't mean there's bridges.
So there can't be 2 bridges?
There could be 2 bridges, but if there are 2 bridges, that means that each individually would have to disconnect the graph, not that they do so together. Okay. So, give you another 30 seconds. Okay. So, I think the answer here is A. Right? Because if you think about a path all spread out here, anything I take from that path will disconnect it. It'll split it in 2. Even if I take an edge on one end, I'll have a single vertex over here and the rest of the path here still disconnected, right? So any edge I get rid of in a path will disconnect it. Now for a cycle, any edge I take will result in a path, but the path will still be connected, right? So I've sort of got this redundancy that if I can't go around one way between 2 vertices, I can go around the other, right? Now, it is the case that if I took 2 edges away from a cycle, I could disconnect it. But that doesn't mean they're bridges, right? A bridge has to be an edge where you remove just that edge and it disconnects the graph. Yeah, question?
What if we remove 2 edges? Would that be 2 bridges?
No, so that's exactly what I was just saying. If you remove 2 edges from a cycle, you can disconnect it. But that doesn't mean those edges are bridges, right? A bridge has to be an edge where you remove just it, and that disconnects the graph. Does that make sense?
Got it.
It needs to, a bridge has to be, you just remove this single edge and it disconnects the graph. Yep. Okay, thank you people, that's all I have for you. Catch you Thursday. Remember set yous and also remember requests for revision topics.